Welcome to The Explainer. Today, we're going to build out a toolkit for every C# coder. Lots of us can write code that works, but we're going beyond that. We're talking about how to craft software that's powerful, maintainable, and, truly well-designed.
And this question right here, this gets to the absolute heart of it, doesn't it? The real art isn't just getting the program to run without crashing. It's about architecture. So let's dive in and explore the core principles that separate good code from great software. And we're going to start right at the foundation.
And what is that foundation? Well, it's all about the data. All great software, every single time, starts with how you choose to store and manage information. So our first tool is going to help us do just that.
Okay, this table draws a really clear line in the sand. On the left, you've got modern generic collections. Their superpower is something called type safety. It means that if you make a list of strings, the compiler guarantees that only strings can ever go in there. No surprises. But on the right, you have the old school stuff like ArrayList, which will take pretty much anything you throw at it. That sounds flexible, but it's really just asking for strange errors to pop up when you run your code. So the takeaway here is simple. For any new code, you always stick with generics.
All right, so our data is organized in these nice, safe collections. But what about the most common data type we deal with day in and day out? Text. So let's pull out the next tool in our kit for mastering it.
I'm talking about regular expressions, or regex for short. The best way to think about regex is like a super-powered search query just for text. It's a tiny language all on its own, designed specifically to find patterns. If you need to validate an email address or pull every single phone number out of a giant document, regex is the tool you reach for.
And regex starts with really simple building blocks. Let's take the dot. The dot is a basic wildcard, and it means any single character. So a pattern like h.t would match hat, hot, and hit, because the dot just stands in for that one spot. Now let's add the asterisk. This is a little different. It's not a character, it's a quantifier. It modifies whatever came right before it, and it means that thing can appear 0 or more times. So it could be there once, 100 times, or not at all. And here is where it gets really powerful. You combine those two simple pieces, the dot, any character, and the asterisk, 0 or more times, and you get dot star. This is the classic go-to pattern to match absolutely everything. It's the foundation for so many complex and useful expressions.
Okay, let's zoom out a little bit. We've handled our data, we've handled text. Now it's time to move up a level and talk about how we actually architect our code, using the blueprints of object-oriented programming.
First up, inheritance. This is all about creating is-a relationships to share code. For example, a car is a vehicle, and a truck is a vehicle. So because they both share that identity, they can inherit things like speed and start engine from a vehicle class. This saves you from writing the same exact code over and over again.
Next, encapsulation. This one is all about protection and control. I want you to picture a protective capsule around your object's data. You don't want other parts of your code to just reach in and change the object's speed whenever they feel like it. Instead, you provide public methods like accelerate and break. This creates a protective barrier, making sure data is only changed in predictable, controlled ways. Now, that idea of inheritance we just discussed, it actually unlocks one of the most powerful and, honestly, coolest concepts in all of programming, polymorphism. Polymorphism literally means many forms, and it is a total game changer. It means you can have a list of vehicle objects, but that list can hold car objects, truck objects, and motorcycle objects all together. Then you can loop through that list and just call the drive method on each one. Polymorphism ensures that even though you're treating them all like a generic vehicle, the specific drive method for a car, or a truck, or a motorcycle is the one that actually runs. It's what makes your code so incredibly flexible.
Okay, so polymorphism is awesome and gives us all this flexibility. But for it to work, we need a way to define the rules, the common ground that all our different objects promise to share.
And this brings us to a really central question that every developer has to ask themselves all the time. When you're designing your classes, do you need a blueprint or do you need a contract? A blueprint suggests a shared identity, maybe with some functionality already built in. A contract, on the other hand, is just a list of capabilities that an object promises to have.
This is the core difference between abstract classes and interfaces.
This table really breaks down the trade-offs. An abstract class is all about sharing implementation. Notice how it can have fields and even methods with actual code. But here's the catch. You can only ever inherit from one of them. An interface, though, is a pure contract. No code, no data. But its big advantage is flexibility, because a single class can implement many different interfaces at once.
So here's the rule of thumb. You should choose an abstract class when your objects are very closely related and share a common identity. If you have a checking account and a savings account, they both really are types of account. So an abstract class makes perfect sense there because they'll share fields and logic. And you should use an interface when totally unrelated classes need to share capability. A document, a customer record, and an image file are all completely different things, but they could all implement an iSavable interface. You see? You're defining what a class can do, not what it is. Okay, so we've designed our code to be flexible and reusable. We've chosen the right contracts. Now for the final piece of our toolkit. How do we make our code robust and able to handle things when they, inevitably, go wrong?
And this is how we do it, with exception handling. This is our tool for gracefully managing the unexpected. Because without it, if your program tries to open a file that doesn't exist or connect to a database that's down, it just crashes. Exception handling gives us a way to anticipate those problems and respond to them intelligently.
And this whole process is managed by the try-catch-finally structure. It works like this. You put your risky code in the try block. If an error happens, the program jumps to the catch block, where you handle it. And then, and this is the most important part, the finally block always runs whether an exception happened or not. That makes it the perfect place for critical cleanup tasks, like closing a file or a network connection.
So, you have the blueprints, you have the tools. By mastering these concepts, from picking the right collections to designing with inheritance and interfaces to building in resilience, you're not just writing lines of code anymore, you're engineering elegant, robust, and lasting solutions. The toolkit is yours, so what will you build? Thanks for watching The Explainer.